we have here a transistor, and this transistor has V threshold of 1 volt. And 1 volt, and gain is 0.8 milliampere volt squared. In A, ID is known 0.1 milliampere, and find RS. So find RS if ID is 0.1 milliampere. So in A, ID is known 0.1 milliampere. So I'm going to assume saturation, and I'm going to verify this at the end. So 0.1 milli equal to Kn over 2 VGS minus V threshold. Okay, Kn is 0.8 to is constant, VGS is unknown, minus V threshold, which is 1. So the only unknown here is VGS. So from that, we can get VGS equal to 1.5 volt. And VGS is equal to VG minus VS. And VG here is the gate. Okay, the current we know it's equal to 0 in the gate, either going into or out. It's basically the same. It's 0. So the voltage drop across this resistance is 0. This point is 0, so this point should also be 0 in voltage. So VG is 0. So based on that, VS is minus 1.5 volt. So the voltage here, which is VS, is minus 1.5 volt. Good. Now, here is ID flowing in that branch. So ID equal to VS minus 5 over RS. ID is 0.1 milliampere. VS is minus 1.5 plus 5 over RS. From that, we can calculate RS. It's easy, 35 kilo ohms. Good, so we get A. Now we go to B. It says, assuming maximum signal swing at the drain, so the output basically at the drain here, find RD. So let's say, draw the sketch the transfer characteristics. So we have here VGS, which is V input, and here is VDS. Here's VDS. Okay, VGS Q, VDS Q, the Q point. But by the way, we don't know VDS here. We know VS, we know VG, but we don't know VD. So since we can span the maximum swing, that means we reach the edge of saturation. So we go down until here. Okay. So this is VDS minimum equal to VGS minimum. Okay. So VDS minimum here equal to VGS. Sorry, not VGS minimum. Let's call it VGS set. It's actually VGS maximum. Let's call it VGS set, because at that point, if the input increases, we're gonna go to the saturation. And remember, VGS is the independent variable. It is the input, okay, and VDS is the dependent variable Y, which is it changes based on the change in the input VGS. So VGS set minus V threshold. Okay, this is equal to VD minus VS equal to VG minus VS minus V threshold. VS will go with VS. So VD is actually at that point, VD is actually VDQ. Okay. Minus 1 equal to still 0. Okay. Minus V threshold, which is 1. So VDQ will be equal to minus 1 plus 1 equal to 0. Okay. Good. So based on that, we know now VD. Okay, so let's look at the circuit here. So VD is equal to ID is equal to 5 minus VD over RD. So ID, which is 0.1 milliampere, equal to 5 minus VD over RD. So 5 minus 0 over RD. So based on that, RD is equal to 5 over 0.1 milli, which is 50 kilo ohms. Okay. Okay, number C. Find the value of GM. That's an easy one. Okay, GM equal to Kn VGS minus V threshold. Everything is known here. Kn is 0.8 milli. I didn't set up, so anyways. VGS is 1.5 and V threshold is 1. So 0.5 multiplied 0.8 multiplied by 0.5, it's actually 0.4 milli ohm minus 1. That's good. Number D now. If terminal Z is grounded, so we're gonna ground terminal Z. And terminal X is connected to a signal source having a resistance of 1 mega ohm. So we're gonna connect here a source signal, V signal, and here is our signal 1 mega ohm. Okay, and the terminal Y is connected to a load resistance of 40 kilo ohms. So there is a load here, 40 kilo ohms. Okay, find the voltage gain from signal source to load, which is GV, the overall voltage gain, V output over V signal. Okay, good. So let's draw the equivalent circuit. I'm gonna start by the transistors GM VGS. Here is the gate, here is the source, here is VGS, here is the drain. And let's connect the other part of the circuit. So between the gate and the ground, there is RG and R signal, V signal. Between the source and the ground, we have RS, but now the capacitor is also grounded, and the capacitor will be shorted. So we shorted the source to ground, so RS will be shorted. So the source will be shorted as well. So this is actually short to ground. Then between the drain and the ground, there are two resistors, RD and RL. Okay, and this is V output. Good. So number D here. So GV here is equal to V output over V signal. And it can be written also as AV, R input plus R signal. And what's AV? AV is V input, which is in here at the terminals of the signal source. Okay. So V output basically is the current, this current multiplied by the equivalent resistance of RD and RL. So minus GM VGS RD parallel RL. And V input is basically VGS. same terminal as VGS. Remember, here is VGS. So this will go with this. So AV is minus GM RD parallel RL. That's very nice. Okay. Now GV is equal to minus GM RD parallel RL. Our input, which is 1 mega ohm. I'm sorry. Yeah, we didn't determine our input yet. So let's do it. Let's do it now. So before we continue, we should determine our input. So our input is the resistance that the source signal sees. When we look from the terminals of source signal, we should see our input. So it is basically RG. So our input here equal to RG. The resistance between these two terminals is RG. Okay. So basically GV is equal to minus GM RD parallel RL. And here are our input, which is RG. So let's call it RG directly. Over RG plus our signal equal to GM is 0.4 milli. Don't worry, because RD parallel RL is in kilo ohms, so that's fine. RD we get it 550 kilos. Parallel RL, which is 40 kilo ohms. This is given in the question. RG is 10 mega ohm. RG is 10 mega ohm. R signal is 1 mega ohm. So everything is known here. So GB is equal to minus 8.08. Okay. So the signal will be amplified 8 times at the output. So we finished D. Now E. If terminal Y now is ground, so let's remove all the stuff, because we're gonna change the input location and the output location. So in E here, now terminal Y is grounded. It was output in E, but now it's grounded, which will ground the drain basically, and the RD will be shorted. Find the voltage gain from X to Z. Okay, so the input is at X and the output is at Z, and Z is open circuit here. So RL is equal to infinity. That's it. So here is the output and here is the input. Okay, good. And basically, if you have the input at the gate and the output at the source, this is common drain amplifier. And common drain amplifier called source follower. And in that case, it actually asked again for also for the output resistance of that source follower, which should be small, very small. Let's do that. Let's draw the equivalent circuit. So this is E now. Let's draw the equivalent circuit. We have GM VGS. Here is the source, here is the drain, here is the gate, here is VGS. Okay. So the drain is grounded, so RD is grounded. RD is shorted or grounded. Good. Now, between the source and the ground, there is RS. And here is basically the terminal Z. Okay, and here is the output, the voltage across RS. And between the gate and the ground, there is RG and the input signal. We have RG and the input signal. Okay, good. So what is required here is a voltage gain. So AV, V output over V input. Okay. V output is the voltage across RS, which is the current in RS multiplied by RS. The current in RS is actually GM VGS because it come here at that node. here is open circuit, so all the current GM VGS will go to RS. So this is equal to GM VGS RS over the input. What's the input? Here is the input. Okay, from that loop, the input is the voltage across RG equal to VGS plus this voltage, which is the output. So this is equal to VGS plus the output. So equal to GM VGS RS over VGS plus the output, which is basically GM VGS RS. So VGS will go away. This is equal to GM RS over 1 plus GM RS. You can write it in that way. RS over 1 over GM plus RS. Why we usually write it in that way? Because usually 1 over GM is much smaller than RS. And in that case, we can approximate the denominator to RS. So AV will be 1 or approximately 1. Although we know all the values, we don't need to make approximation. So let's make the compensation and calculate it. So basically, AV will be equal to 0.933. Okay, and it's positive. It's non-inverting. Common drain is non-inverting. Okay. Good. Now RO. So for RO, we're gonna imagine we have Vx and Ix source at the terminal of the output, and we short the independent sources, which is the input in that case. So we're gonna short the input. So we're gonna just make a short circuit instead of it. So let's make it in another color even, for example. Yeah, and we're gonna imagine here we have the input and the input, or Vx and Ix, whatever you call it. So RO here equal to Vx over Ix. Okay. Okay. Basically, Vx is the voltage across RS. Okay. And if you look at here, RG is actually shorted. So we can just remove RG because it's shorted now. And when you do that, the gate will be grounded. Okay. And remember, RS is between the source and the ground, right? And the VGS now is all the time between also the source and the gate. And the gate is now the ground, right? So basically, if you make a loop here, this loop, you will have only 2 voltages in that loop. The voltage across RS, which is Vx, and VGS, okay? And they both in the same directions. So Vx is basically minus VGS. This is equally minus VGS. How about Ix? So Ix is going into the node here, okay? And here is so I input Ix is going to that node. GM VGS is also equal to that node, going into that node. So GM VGS. Okay. I'm sorry. Yeah. So this should be minus. Okay. Yeah, this should be minus because Ix is equal to that the current that is going out of the node, which is the current across RS, minus the current into the node, which is GM VGS. Okay. So the current in RS is Vx over RS. And Vx is minus VGS. So this is again minus VGS over RS. So if you just confused, so at that node, the currents going into the nodes Ix and GM VGS. The current that is going out of the node is IRS. Let's call it IRS. IRS is equal to the voltage across RS over RS. Vx over RS. Vx is minus VGS. So this is minus VGS over RS. So basically Ix equal to minus VGS over RS, I'm sorry, minus GM VGS. That's what we have here. Nope. Exactly the same. Okay. So the minus will go away. VGS with VGS also will go away. So RO equal to 1 over GM plus 1 over RS. Okay. And if you calculate this, it will be very small, 2.33 kilo ohms. Yes, it's very small if you compare it to our input, which is 10 mega ohms. Yes, it's very small. You know. Good. So we finished also number E. Now number F, and again we're gonna remove all what we have done. So draw. Okay. Now in that case, in F, X is grounded. And the terminal Z is connected to a current source. So we're gonna connect a current source here. And this current source is dribbling 10 microamperes and have an internal resistance of 100 kilo ohms. You remember, guys, you know, in the internal resistance of a current source is in parallel with the current source. It's different from the internal resistance of a voltage source. The internal resistance of voltage source is the source in series with this internal resistance. For current source, the internal resistance is in parallel with the current source. Okay, so if this is the internal resistance, let's call it our signal. Here is I signal. And both are connected to terminal Z. And the output here at Y. And what's required here is the maximum voltage at Y, the out maximum. Okay, if this is maximum 10 microampere. Okay, let's again draw the equivalent circuit. And here is the first time we see a current source basically instead of a voltage source in the input as I see. Here gate, drain, and the source. And the source here we have, for the source, let's go back and check what we have. We have RS between the source and the ground. We have RS, we have our signal, we have the 10 microampere, all that in parallel. So we have RS. We have our signal, which is known, 100 kilo ohm, and we have I signal. And I signal is known. The maximum value of I signal is known, 10 microamperes. So I signal max. Microamperes, and our signal is 100 kilo ohm. Okay, what is the rest of the circuit? Between the drain and the ground, there is RD. And the output is at the drain. And the gate is actually connected to zero, to ground. So RG will be grounded or shorted. So here is the gate, it is grounded. And here is VGS. Okay? Yeah, that's it. And here is RS. And RS is known. Okay. So let's call this current here I input. And let's call this IRS. Okay, and I've called it here the GM VGS. Okay. If we look between these two terminals, this terminal here is the source and the ground, we're gonna see, you know, an input resistance. Let's call it, or R7, whatever you call it. Let's call it our input. Okay. So let's determine this our input because we're gonna use it. Okay. So if we determine our input, we're gonna assume here we have Vx and Ix. I will leave all that headache to you guys. Okay, so you remove basically this part, the R signal and I signal. You put Vx and Ix. It will be easy to determine. So our input will be 1 over Gm plus 1 over Rs. And actually, this is exactly this one. That's why it's the previous. It's actually would be the same. If you just imagine that you remove this and you put Vx and Ix, this will be turned into that circuit. Okay, so we already did it. Okay, and we know also the value 2.33 kilo ohm. Okay, but why we did this? So if we can remove all of that and put its equivalent circuit, we're gonna have something like this. I signal, our signal, and our input, which we know now. And here is our input. Okay, this I input, this current. So I input from circuit theory equal to I signal, the total current. I input is a current flowing in one of the parallel branches. So it's equal to I input, the total current, multiplied by it's flowing into our input, so multiplied by the far away resistance, which is our signal, over our signal plus our input. It is an opposite, you know. It's flowing in R1, so you would put R2, you know, something like this. Remember, we know our signal, we know our input, we know also I signal, so we can determine I input. Okay, so I input is 9.77 microamperes. Okay, basically, if you notice, this guy has maximum 10 microamperes, so most of it goes to our input. Why? Because our signal is 100 kilo ohms, while our input is very small, 2.33 kilo ohms. Okay, that's why most of the current goes to our input, which is good, by the way, because this is our source now. We want most of its current to go into the amplification circuit, not its internal resistance. Good. So what's after that? Yeah. Now we determine I input here. So let's go back to the original circuit. So let's draw this with. So we know our I input. So at that point or at that node, okay, I input is going into the node. GM VGS is also going into the node. And the IRS is going out of the node. And the IRS is equal to the voltage across RS, which we don't know, over RS. Okay, good. What is VRS? VRS, the voltage across RS, is actually the voltage of the source, right? Because one terminal is ground and the other terminal is the source. Good. If we go back with I input is flowing in our input, and our input has two terminals. The source is one of the terminals, and the other terminal is the ground. So the voltage across our input is actually the voltage of RS. So VR input is actually VRS. But what is VR input? VR input is basically I input multiplied by R input. That's why it was really crucial to determine our input. It will make your life very easy. So 9.77 microamperes multiplied by 2.33 kilo ohms. So this will give you 22.76 millivolt. Okay, then we can determine this is VRS. That's So we can determine basically IRS. Okay, so I input is known, 9.77 microamperes. GM IRS is also known. We don't need to determine VGS alone. We can just determine the whole voltage GM VGS. Okay, so GM VGS is equal to, if we compensate, it's equal to minus 9.11 microamperes. Okay, and what is the output now? So the output is equal to minus GM VGS. Here is the output. So it's equal to this current, which is flowing from bottom to up. So it makes a voltage drop positive, negative, opposite to the output. So the output is equal to minus GM VGS multiplied by RD. Okay, the drain resistance, which we determine is number B. GM VGS is minus 9.11. So this is 9.11 microamperes multiplied by RD, which is 50 kilo ohms. This will give you 0.455 millivolt. Okay, guys. So this was basically the last requirement in last question here in this exam. This is really a very rich example. It has a lot of ideas. You know, it gathers a lot of concepts. It actually gathers, you know, common source, common drain, common gate in one circuit. Thank you very much.